All right. Pen. All right, I don't know how to make that screen work, so hopefully those of you sitting over there can see just fine. Today is July 2nd. Happy July, everybody. And we're going to start chapter 2, exponential functions, with a review of exponential notation. So basically today's mini lecture is going to be mostly about mathematical grammar. So for example, examples of exponential notation. Right? It's really just a way to keep things compact. If I have 3 to the 4th, that's 3 times 3 times 3 times 3, which is 81. All right, so this is our exponential notation right here. Instead of writing 3 times 3 times 3 times 3, we write 3 to the 4th. That's what that implies. If I write, let's see, 5 times 5 times 5, and I want to write it as exponential notation, there's 3 of those 5s, so that's 5 cubed. And your calculators can do those multiplications pretty easily. I could do something like 1/2 to the 5th. And there are 2 ways to think about doing this. The first way is to recognize that I'm multiplying 1/2 by itself 5 times. And when you multiply fractions, you multiply the top and you multiply the bottom, and you get 1/32. Or I could see this as 1 to the 5th over 2 to the 5th, because you distribute an exponent across division. 1 to the 5th, or 1/2 to the 5th is 1 to the 5th divided by 2 to the 5th, which is also 1/32. All right, those are our basic examples. We have some rules of exponential notation. First rule is if you take a number to a power and multiply it by a number to another power. I don't use that one. I use 4. You get to add the 2 powers. And we can see that's true because 3 squared is 3 times 3. And 3 to the 4th is 3 times 3 times 3 times 3. And that's just 6 3s all multiplied together. I think that's 729. But I'm not sure. That's what calculators are for. So often you'll see this written not with numbers, but with letters. But let me do another example with numbers first. Let's look at 1/4 squared times 1/4 cubed. That's 1/4 times 1/4 times 1/4 times 1/4 times 1/4, which is 1/4 raised to the 2 plus 3 or 1/4 to the 5th power. So that the general rule here is that 3 is called the base, and the 2 is the exponent. Also the base, also the exponent. So same base multiplied, add the exponents. And so you might see it like x to the a times x to the b equals x to the a plus b. Same base multiplied, add the exponents. Well, if you have the same base with division, you subtract the exponents. For example, if I have 7 raised to the 5th divided by 7 raised to the 3rd, I could write that as 5 sevens multiplied together on top, divided by 3 sevens multiplied together on the bottom. And then we get to cancel the common sevens, and we're just left with 7 times 7, which is 7 to the 5 minus 3, or 7 squared. Same base with division, subtract the exponents. So you might see this something like y to the a divided by y to the b equals y to the a minus b. Okay. This actually gives us a way to define negative exponents. Let's look at 5 to the 3rd divided by 5 to the 7th. That's 3 5s multiplied together on the top and 7 5s together multiplied together on the bottom. We cancel what we can. We can only cancel 3 of those 5s. That leaves us with a 1 on the top and 5 multiplied together 4 times on the bottom. Now, if I use my same base division, I would say that's 5 to the 3 minus 7, because you subtract the exponents. Well, 3 minus 7 is -4. So 5 to the -4 is the same as 1 over 5 to the 4th. A negative exponent can be written as a positive exponent if you move the base, that's the 5 in this example, if you move the base from the top of a fraction to the bottom of a fraction. And actually, or vice versa. So let me give you some examples of that. 3 to the minus 4, I can write as 1 over 3 to the 4th. 1 over 2 to the 7th, I can write as 2 to the minus 7. And in fact, 1 over 5 to the minus 3, there I'm in the bottom with a negative exponent. I can make that exponent positive if I move the base from the bottom to the top. And I can flip whole fractions as well. If I do 2/3 to the minus 8, that would just be 2/3 multiplied by itself 8 times, but in the denominator. I can think of that as 2 to the minus 8 over 3 to the minus 8. And now I can write the 2 with a positive exponent if I put it in the bottom. And I can write the 3 with a positive exponent if I put it in the top, which gives me the flipped fraction known as the reciprocal, now with a positive exponent. And so you flip the fraction, you change the sign of the power of the exponent. There are lots of other tiny little rules that you could learn that come out of things like this. Too many, I think, to cover. Some is just about discovering yourself. If you kind of come back to these more general rules, sometimes you can discover other ones. All right, we've talked about basic positive exponents. We've talked about basic negative exponents. We can also have 0 when 0 is the exponent. Like 3 to the 0. That's 1. Any base with 0 as the exponent equals 1. And that's just because 3 to the 0, if I wanted to be clever, I could write it as 3 to the 2 minus 2. Because 2 minus 2 is 0, which is 3 squared divided by 3 squared. 3 times 3 over 3 times 3, and all of those cancel, and it gives me 1. So you might see this as x to the 0 equals 1 for any x. And 2 more kind of basic definitions. X to the 1 equals x for any x. All right, that's just x by itself. And x to the minus 1 equals 1 over x for any x. Okay. Anybody have questions so far? Now, these are a set of rules. You can always, as you're doing this, if you find you don't have your notes, right, you can just go on the internet and say, Google, give me the list of rules for exponents, or ChatGPT, what's the list of rules for exponents? And it'll create a very similar list. It might not use X, it might use A, but the principles will be the same. All right, couple more rules for exponential notation. Exponents distribute across multiplication and division but not across addition or subtraction. Distribute means you can take the exponent and put it on both of the terms or all of the terms. So I'll give you the 4 examples and make sure I give myself room. Let's do 3 times 8 squared. Well, that's 3 times 8 times 3 times 8. And with a little rearranging, that's 3 times 3 times 8 times 8, which is 3 squared times 8 squared. That's squared distributed across the multiplication. You square each of those terms. Division, let's do 5 over 7 cubed. We talked about this already. That's 5 cubed over 7 cubed. Let's look at addition now. Let's look at 1. No, let's not look at 1. Let's do 2 plus 3 quantity to the 4th. Well, that's PEMDAS says we do what's in the parentheses first. So that's 5 to the 4th, which is, I happen to know, is 625. Compare that to trying to distribute 2 to the 4th plus 3 to the 4th. Well, that's 16 plus 81, which is 97. Definitely are not the same numbers. This equal sign with a line through it means not equal. You cannot distribute powers over addition. And you also can't distribute powers over subtraction. I'm going to give you a super simple example of that. 7 minus 7 squared. No, that's not a good one. How about 7 minus 6 squared? 7 minus 7 squared is the one time that it would work. Oops. There's usually exceptions. 7 minus 6 squared, well, that's just 1 squared, which is 1. But if I were to try to distribute that and look at 7 squared minus 6 squared, that's 49 minus 36, which is 13, which definitely is not equal to 1. You have to be careful with your powers. Powers distribute across multiplication and across division exponents, but they don't distribute across addition or subtraction. All right. Couple of subtleties that I want to point out to you. So let's do, I'm going to do an example. 5x to the 4th times 9x squared. You collect the same bases, then figure out powers. So I would write this as if it's 5x to the 4th times 9x squared. 5 and 9 are both numbers, so I consider those the same kind of base. And then x to the 4th and x squared both have x as a base. I do my regular arithmetic on the 5 times 9, which is 45. And I add the powers of the x's. I add the exponents of the x's. And you can do that even if you have 20 different types of bases. I could have 5x squared, y to the 9th, z to the 3rd, q to the 18, right, times 9, x to the 12, y to the minus 8, z to the 13, q to the 4, or something. And I'll just collect each of those terms. Okay, that's one subtlety. Another subtlety is -2 cubed is not the same as -2 cubed. So parentheses matter. For exponents. -2 quantity cubed. Oh, darn it. I picked another one where it's the same. So let's do a fourth. Then they won't be the same. I think, Scott, you're a bad luck charm. You laugh every time I mess it up. Or a good luck charm.
I don't.
Okay, -2 to the fourth is -2 times -2 times -2 times -2. What's a negative times a negative? Positive. So this is -2 times -2 is 4. And that other -2 times -2 is 4, which gives me 16. But if I don't have the parentheses, and it's -2 to the fourth, PEMDAS says I do the exponent first. So that would be -2 times 2 times 2 times 2, which is -16. So parentheses matter when you're doing exponents. Sometimes it works out to be the same. If I had done cubed, it would have been fine. It would have been -8 on both sides. But with that even exponent, -2 quantity to the fourth is 16. -2 to the fourth is -16. Okay. Next. Base raised to an exponent raised to another exponent. So let me give an example. 3 squared, and I'm going to raise all of that to the 5th power. That's going to equal 3 to the 2 times 5, which is 3 to the 10th. So you multiply the exponent. Three squared is 3 times 3, and I'm going to do that 5 times. And so I have 10 threes multiplied together, which is 3 to the 10th. What if I have 2 to the 4th raised to the -3? The multiplication of exponents tell me that's 2 to the 4 times -3, which is 2 to the -12, which should be 1 over 2 to the 12th. Process is the same, but now there's a lot of these intermediate steps to keep track of. Any one of these 4 equalities is a perfectly valid representation of this number, as is 4096, as is this one. These are all equivalently equal. Now on a midterm, I might ask you to say, take 2 to the 4th raised to the -3rd and write it as a number with a single positive power. Not yet. Not yet. Yep, that works. So I'm going to want you to be able to move between these different symbolic representations. The good news is if you put this into your calculator the right way, or you put this into your calculator the right way, it's going to give you the same decimal approximation. Okay, so you're going to get a chance to practice those. You might run into a couple that feel like you haven't seen them yet, but that's why Gabe and I are here. Next topic. Scientific notation. People and sometimes calculators are lazy. We don't always want or need the full number. So we write it using what's called scientific notation. You're going to see this most if you do engineering or biological science, especially chemistry, because chemistry deals with supergiant numbers. You know how many atoms are in a gram of uranium? A lot, right? Enough that you don't want to write out that whole number. So scientific notation takes a long number and collapses it down. So for example, instead of 400, I could write that as 4 times 100. Agreed? And 100 is 10 squared. So I could actually write that as 4 times 10 squared. And that right there is scientific notation. And if you ask me, that took longer than writing 400. But if I wrote 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I wrote, what is that, 40 trillion? It'd be a lot faster to write that as 4 times 10 to the 10th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. This is scientific notation. It's faster. How do you write scientific notation for big numbers? Yeah. Count the number of places from the ones unit until the second to largest unit. So here I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 places from the ones unit to the second to largest unit. So that's 4 times 10 to the 10th. Just like in 400, I have 1, 2 is 4 times 10 squared. Or you can think about move the decimal over and count how many steps. So let's take a look at what that means. Let's say I don't have 40 trillion, but I have 41,932,678,405. That could be like, I don't know, number of bacteria on my Petri dish. Do you think I'd really count that specifically? No, but let's say I could. So I want to write this as scientific notation. So I count the number of decimal places I have to move. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Start your decimal place here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 4.1932678,405 times 10 to the 10th, because I moved it 10 decimal places. Of course, nobody's going to do that because we're lazy. If I'm going to write out that length of decimal, might as well write out that length of number. So instead, I say, well, that's approximately 4.19 times 10 to the 10th. The main reason to use scientific notation is to cut down on your work by saying, I mean, does it really matter if I have 41,932,000,000,000 or 41,936,000,000,000 bacteria? Doesn't, right? It's close enough. So we truncate and we write it in a compact form like that. And we can move the other way as well. So let's suppose I have a decimal now, 0.000718. I do the same thing. I'm going to move the decimal place until it's just to the right of my first non-zero number. 1, 2, 3, 4, 5. 5 moves. And so that becomes 7.18 times 10. I moved it 5, but I moved it to the right. So I do a minus 5 up here. And that's my scientific notation. Like I said, today is all about kind of building some of those basic notational skills, right? I would say we're not really doing much mathematical thinking here. We're just kind of learning our grammar. So when we use these types of expressions in the future, we can keep track of the different ways they're written, or maybe go from one to the other so that our math can be more efficient. Let me do one more. 0.09138062.1. And again, I don't need to write out that whole decimal. Does it matter if I have 0.0913 or 0.0914? Honestly, it probably doesn't, unless maybe you're working for NASA and this is a heat tolerance, in which case you just include all the decimals. I'm going to move it just 1, 2 spaces. So that becomes let's do 9.14 times 10 to the minus 2. And I can do an approximate there. Okay. Any questions about scientific notation? All right, last topic for today is fractional exponents. If you look back through your notes, you're going to notice so far our exponents were either whole numbers or negative integers, right? They were 1, 2, 3, and 4, or -1, -2, -3, or 0. But we didn't have to the 1/2. We didn't have to the 1/9. So these are also called roots or radicals. So let's start off with the square root of 9. That's maybe one verbal way of representing that idea. And the symbol we use for that is the square root symbol. I don't know how else to say it. This is the positive number that squares to 9. And what is that positive number that squares to 9? 3, because 3 times 3 is 9. 3 times 3 is 9, and 3 is positive. Technically, there's another number that squares to 9, which is -3. But when we use a square root, we're asking for the positive. Now, we can write the square root of 9 using an exponent that follows all the rules we already developed. Where if you have the same base and you multiply together, you add the exponents. Where if you want to make it negative, you put it in the denominator, where you can do all sorts of things, right? It'll follow all those same rules if we recognize that the square root, which comes from 2, right, because 3 squared, means the square root of 9 can be written as 9 to the 1/2 power. That's just notation, but we're lucky because this notation gets to follow all the rules we developed. Let me just give you one example of that. 3 times 3 equals 9, which we know. 3 is the square root of 9. So that means the square root of 9 times the square root of 9 must equal 9. That's exactly what it means to have the square root. And if I write that as 9 to the 1/2 times 9 to the 1/2, my rules of exponents say I get to add those exponents, which is 9 to the 1st, which is 9. Right, so the fractional exponents allow us to use all the same rules with square roots that we get to use with any other exponents. Right? That was the square root, but you can do any fractional exponent. Like 64 to the 1/3 is the number that raised to the 3rd power is 64. A number times a number times a number equals 64. All right, so x times x times x equals 64. Means x is 64 to the 1/3. That happens to be 4, because 4 times 4 times 4 equals 64. So 64 to the 1/3 equals 4. Most calculators have a general root function. We can write this using the root or the radical symbol. (64 to the 1/3). We do the radical symbol of 64 and we put the 3 up there. And that means we're raising it to the 1/3 power. Okay, and we can combine fractional powers exponents with integer exponents. Let's look at an example of that. Let's look at 5 squared. And now let's take the 7th root of 5 squared. I know the 7th root is the same as the 1/7 power. So I can write that as 5 squared in parentheses raised to the 1/7. And then I can use my rules of multiplication to get 5 to the 2/7. So if you have combining a fractional power with an integer exponent or a radical with an exponent, you can write it as a single fractional power where the integer exponent, the 2, goes on top and the root, the 7, goes on bottom. That's all I have. You may come across a couple more ideas as you work through it, in which case I'd be happy to help. All of that can be found in the packet that I handed out on Monday. Is anyone not here on Monday who doesn't have a packet? All right, I'll get one for you. Let me stop the video.